All right, part D of this problem. And I won't go through it in quite as much detail maybe as the last few. And partly these are a little longer because I'm trying to make this a video where if you aren't familiar with how these solids look yet, we're trying to get a feel for that too. I'll make some videos in the future where we go a little faster through some problems if you're at the point of just wanting to get some fluency. These are more introductory videos. So this one, we're trying to revolve this solid now against about a horizontal line again. We did it in part B, we did it about the x-axis, which is a horizontal line. But this one's a little different because now we're going about the line y equals -2, which would be, maybe, oops, don't have the pen tool, maybe around there. So we're going to revolve this region about that horizontal line. So we're going to have those rectangles going vertically again. But now instead of going about the x-axis and making washers like this, now we're going to go further to go around the line y equals -2. And so it's going to be further down. In fact, here, let me give myself some room here. Well, I guess I should get rid of that line first. And it's going to go down even further than what I've got showing here, really. Kind of more like that. Not my best work, but you get the idea, I think. And so it's going to be a bigger ring than we got about the x-axis. And in fact, when we did it about the x-axis, it actually met up with itself at 0. So it wasn't even fully see-through if you looked at it sideways, like from this angle or this angle, because this circle was a disk at the very end that was solid. Okay? But now, because we're going about the line y equals -2, there's going to be a hole through it all the way through. So I do have this set up on Desmos also. Let's take a look. So here's that region again in the XY plane, outlined in red, shaded in gray. And you can picture that ith subinterval, which I have here. And this is showing the washer for the ith subinterval going around the x-axis. So look at where the z is going up now. It's kind of hard, the tools on Desmos 3D to kind of get it how I want it. But that's that washer going all the way around. That's one part of the solid. So let me put in the full solid now. There's the full solid in red. And that blue part is that one washer, the ith subinterval. And so here, looking straight on at the xy plane, we can move that blue washer through the solid, the ith subinterval. And the idea is, again, we're like doing all of these different subintervals as you go through, right? So here's that blue washer from an angle here. And then if we get rid of the full solid and just look at the washer, there it is. And it's, this is we're like adding together all these little washers to fill out the entire volume of that solid. That's what the solid looks like. Just like that. Okay? So hopefully you got a picture there of what it looks like, a visual that's good enough. And so again, since we're going about a horizontal line, the width of our washers is a distance on the x-axis. It's going to be a delta x or a dx when we integrate. Sorry for the bad writing there. Low on this board, it's not great. So dx, it's with respect to x, not with respect to y. So we're back to these functions, y as a function of x. In part C, when we went about a vertical line doing with disks and washers, we had to do dy. Whenever you're going about a horizontal line with disks and washers, we're going to do dx. So again, this top curve is, I believe, was called f of x. It equals the square root of x plus 2. And then this bottom curve was just g of x equals x. And let's set it up. We're going to get the volume. It's going to be an integral. I'm leaving room for pi in front because we're going to need that. In fact, I'll just put it now. We're going to integrate from 0 for an x value up to 4 for an x value. And again, the area of the washer, I'll get rid of this in a minute, but the area of any of these washers is pi times the big radius squared minus pi times the little radius squared. That's a lowercase r I'm writing there. And so the area, cross-sectional area, is A equals pi times big R squared minus pi times little r squared. Okay? Our big R here and our little r, they're a little trickier because we're going about the line y equals -2. So we'll talk about that in a second. But we're still using these two functions as part of that radius. So that's what we have to ask ourselves. What is our radius of revolution? Okay? But this is the formula to get the area of the washer, the area between these two circles, right? It's the big circle minus the little circle is the idea. All right, so let's do it. The outer radius, big R, is the distance from the outer curve when I'm revolving it, whatever the outer curve is, to the axis of revolution. It's this distance here. So it's this outer curve f of x minus the axis of revolution, which is y equals -2. It's f of x minus -2. And you might have been thinking, you might have been thinking f of x to here, and then plus 2, because it's like 2 further. And that's obviously it's the same thing. So that works, but the reason I'm saying minus -2, it's very formulaic this way. It's just the curve minus the axis. Okay, or it could be the axis minus the curve if the curve is underneath. And for big R, we're going to use the outer curve further away from the axis. Okay, so the stuff I'm saying right now is general, and it'll apply to different problem situations too. So any solid of revolution, we want pi times big R squared minus pi times little r squared. So we want pi times the outer curve minus the axis quantity squared. In this case, that's going to be f of x minus -2, so plus 2, quantity squared, minus pi times the inner radius, the inside radius, which is the inner curve, minus the axis of revolution. So g of x minus -2, so plus 2, quantity squared, and then dx. That's the setup. That's it. It's very formulaic. Once you do a few of these, you really get the hang of it. And I'm not going to be able to just shrink that, so whatever. Let me get rid of this stuff. I'll use the eraser so I don't get rid of other stuff too. And let's do this integral. And I didn't totally plan this all out when I wrote the problem. And in part C, the algebra got a little funky, or the arithmetic at the end. This one might too. I'm not totally sure. We'll see. But we'll do it till it feels like we should just stop. So we have pi times the integral from 0 to 4. And then f of x is the square root of x plus 2. So if I want to kind of rewrite that, this is the square root of x plus 2 plus 2. So plus 4 is what's getting squared there. And then g of x is just x. So that's just x plus 2 squared is what that's going to be. So let's go ahead and expand those out. So we're going to have, when you square square root of x plus 4, you're going to get an x. You're going to get an 8 square root of x, or 8 square roots of x. And then you're going to get a 16. And then subtract. And I'm just going to distribute as I go here. X plus 2 quantity squared will be x plus 4x plus 4. So it'll be minus x squared minus 4x minus 4. And then dx. Yeah, this one isn't too bad. So we'll go ahead and do that integral now. The antiderivatives here. If you could combine like terms first. I guess we should do that. It'll be less work. I'm all for less work. So the highest degree term is the negative x squared. I'll put that first. Then the x term is going to be minus 3x, because I have a minus 4x and a plus x. And then I have an 8x to the 1/2. And then I have the minus 4 and plus 16, so that's plus 12. dx. Okay, now I'm going to go ahead and do the antiderivatives. And so we get negative 1/3 x cubed. And I'm not going to forget that pi. We'll put it on at the end. The next term, minus 3x, that'll be minus 3/2 x squared. The next one, that's going to be an x to the 3/2 multiplied by 2/3. So we're going to get 16/3 when you multiply by the 8. There's a plus in there. And then we have plus 12x. And again, this is evaluated from 0 to 4. And there is a pi multiple. Again, don't bother with the pi. Like, no need to keep writing it on every term. I just keep it factored out until the end, and then try to write as simply as I'm going to write my answer. This one with a 0 is nice because when you plug 0 in, you'll get all zeros for this one, since it's all power functions on x with no negatives. Anyway, so we'll just really plug the 4 in. When we plug 4 in, we're going to get negative 64/3. And then we have minus 3/2 times 16, that's 48/2, which is 24. And then we've got plus, and 4 to the 3/2 power. So take the square root first and get 2, and then 2 to the 3rd is 8. 8 times 16 is 128. That's a 2 to the 7th. So that's going to be 128. Here, let me get rid of that circle. 128 over 3. And then the last part is going to be plus 48, 12 times 4. And then if we do minus and plug the 0 in, all of these terms will give us 0 when we plug 0 in. You do want to pay attention and make sure, though. And it's pi times that. And now we can simplify. The 128 over 3 minus the 64 over 3 is 64 over 3, because it's 2 to the 7th minus 2 to the 6th over 3. So 64/3, and then plus, and this is just 24 when you put those together. I'm going to make it 72/3 so that I can give one answer here. And just a little more here. 72 plus 64 is 136. So we have 136 over 3 pi. And you could divide in if you like and get like a decimal or a mixed number if you want to have like an idea of what that is. Or, even better, really rough estimate, pi is a little more than 3. So when you divide it by 3, it's a little more than 1. So the volume here is a little more than 136, probably like 140 to 150, somewhere in that neighborhood. Or maybe even 150 to 160, somewhere in there. Anyway, that's it. That's the final answer here for this question. Hope that was instructive, and I plan to make some more videos on this, maybe with axis of revolution that's above the region or to the right or left of the region, but it's not the y-axis. And then also I'm going to make some videos where we have solids with a certain shaped cross-section. Those will come too. I might even stick with the same region R to do those.